I started here in August of last year. And a lot of this work that I'm going to talk about was done by Rachel, and I'll talk a little bit about. Sorry, guys. I'll talk a little bit about the things that I've done, I'm working on, and that Steve and I are planning to do in the future. I also am hoping to get feedback. I have some printouts of some things that I'll hand out at the appropriate time. And feel free to just stop me if something doesn't make sense, or if I'm rambling, or if I'm talking for too long. Just go ahead and stop me. So I think Ben said this best when he said, you can't give an SEI talk without showing this. So here is the SEI transformation model, which I didn't really understand well until I wrote this talk. And it's very broad, it's very nice, and I'm framing the talk around this triangle and how we're sort of doing all of these different pieces. So if you haven't seen this before, I'd be a little surprised. So the first piece of this is sort of what should students learn? What do we think that they should learn? And we can form that in any of our courses, but in classical mechanics in particular, we were looking at consensus learning goals. And what does that mean? That means essentially talking with faculty about what they think students should be able to do, rather than what topics should I cover in the course. What are the sort of outcomes that I want? And this was work that Rachel did, where she brought faculty in to, I think, a total of maybe 7 meetings, and had them sort of express what are the different things you want students to be able to do broadly when they leave the course. And also when we start talking about individual topics in the course, what are the types of things they should be able to do. So let me just give you an example of that really quickly. So this would be what I would call a course scale learning goal. That is sort of a very broad goal for students. They should be able to recognize when a series expansion is appropriate to approximate a solution and expand the Taylor series beyond 0. So it's very broad. There's a lot of stuff in there. There's a lot of things you have to unpack that students should be able to do. And that's where the topic level goals come in. So this would be a topic level goal that deals with Taylor series. Students should be able to take the Taylor series expansion around 0 for common functions and express the solution both as a list of terms and as a series. So now we're being very concrete. The topic level goals are ones I think that are more measurable than the course scale goals. Those are somewhat broader. Now, these learning goals were only presented to, I think, our faculty. Is that right, Steve? That it's sort of internal. So there's still this idea of, well, once this goes external and we start talking to other people, are these still valid? Are these still useful? So that's something I'll come back to in a minute. The other thing I want to point out is I'm going to highlight Taylor series kind of a lot because we're doing a lot of investigations in it, and that's sort of where I'm looking for feedback. All right. The next piece of this triangle, the way that I organize it in my head, is what instructional approaches improve student learning. And a lot of the stuff that we've done in this course, that again was done before me, but I'm continuing to work with Steve on it, is developing tools that are used in introductory physics for upper division. And so things like pre-flights, concept tests, tutorials, homework that emphasizes sense-making, estimation, these other skills that typical homework doesn't, and having, instead of office hours, homework help sessions. So having students come in and work together, and we're sort of floating around and coaching rather than one-on-one instruction with the student. So I'm going to give a couple of examples of that. This first part of the talk is really just sort of an overview. So here's an example of a pre-flight. You might just get the idea. So what students would do with this is, before class, they're asked to read the textbook, and there's a connection here made between an example in the textbook and an example which Steve worked out in his notes, and he sort of asked if there's any differences. This is the same sort of style. We generally try to point the students to the text to make sure that they're going through the text before class, and it also helps us to do a little bit of just-in-time teaching, so we get some of these answers. We can see if there's commonalities among students' misunderstandings, and we can address those in class. So pretty standard. Here's a concept test for those of you who are rusty.
Are those pre-flights done online?
Yes, they are. They're done online. So we were doing these before using just regular HTML and some scripts, and now we have just moved to using Desire to Learn, because both Steve and I have the desire to do that. So, that was tough, actually, to get those sort of integrated properly so that they didn't look like quizzes. We didn't want them to look like quizzes. We wanted them to just be like a survey. So that's working now. So.
Yeah. we don't know if that's the right strategy or not.
Right.
I mean, I assume that most faculty at Colorado will be using D2L, but on the other hand, it's not very useful for people outside of Colorado.
And this is something that you can survey right before class.
It's due, so we have class on Tuesdays and Thursdays at 12:30. It's due at 10 a.m. on Tuesday. So right before class, we look at it. Okay. So here's an example of a concept test or a clicker question that's given in this class. So students might be learning about Fourier series, and they have these Fourier coefficients, and there's some sketch here, and they're asked about, what can you say about the different Fourier coefficients? And there's some instruction here on symmetry. There's actually a tutorial about it as well. So this is just some, interesting concept test that we have. This is part of the tutorial. Can everybody read this? Because this is the lowest font size that I go down to. Can everyone read that? Okay. So this is a tutorial that we wrote last semester on line integrals. And one of the things that we thought that students might be having trouble with is sort of how you pick the appropriate path. That's something that when you're doing line integrals, you generally don't actually do the calculation. The physicist tries to sort of visualize the field and then decide what is an appropriate path and then exploit that path for a conservative field, mind you. So here's a tutorial, part of a tutorial where students are given a vector field, 2 positions, and asked to sketch their best choice of path for that line integral. They're told that the fields are conservative, and then they discuss with their group members and try to characterize those paths. What can they pull out of that to help them figure out what the best choice of path is to reason sort of qualitatively about line integrals.
Are these explicitly tied to the learning goals then that are set up? I mean, have we indexed problems and tutorials to things like exploit symmetry?
That's a good question. No, that hasn't been done to my understanding for the clicker questions, homework questions, and so forth. It would be something that could be worth doing. But I will show you in a moment that maybe it's something that we don't really understand very well because
right, well, this goes back to sort of Bethany's work. Anyway, this was a small question that we can elaborate on later.
Okay. Yeah,
I think it's a big question.
It's a big question because it comes up with the assessment, which I'll show you guys in a minute.
Well, it's an important question. It was a small question.
Okay.
It's a lot of work. Right? It's big. It's a small question, but it's big work in it.
Well, are we going there?
Let's go.
All right. So, I mean, the point is this question is there for a reason. When this was written down, somebody thought, hey, I'm going to put this here for a reason, but that reason hasn't been externalized, is sort of what I'm suggesting. And that doesn't mean that it answers or it shows up in the assessment that this impacts students' abilities, which is sort of what Bethany was is starting to noodle at. If you noodle at things, I don't. Anyway, but point is at what point do we want to externalize these kinds of links?
Right. I think it brings up an important question: is that are the learning goals driving the creation of these questions and so forth, or is it sort of that? Are we kind of doing it piecemeal and then trying to make those connections later on?
No, it's a good point. So this was actually driven by what we observed in homework sessions, not by the learning goals. It was what we observed students having difficulty with. And I believe when these learning goals were formed, there was not a lot of discussion. I mean, there's sort of I imagine there was a discussion about what students had trouble with, but it wasn't dealt with in the way that we do research on it. Is that right, Steve? So
As I recall, there were some high-level learning goals like exploiting symmetry and setting up
That's
problems
correct.
that you
Right.
really associate.
Right, but sort of.
There's specific goals for mechanics too.
Yeah. But it might be something that actually requires an iterative design approach just with everything else that we're doing is we start to observe these difficulties and now these sort of influence what the goals might be, which I'm not sure that has been done. I mean, it hasn't been done since I've been here, so we're iterating on that.
So Rachel did one set of observations and then drafted specific goals for the faculty. So she probably had some difficulties in her mind when she was writing.
Okay. Great. All right. So this leads to sort of the last piece here. So you've decided what students should learn. You have the tools with which you think students should use to learn, and then the question is, what are students actually learning? And I see this as sort of 2 pieces. There's direct investigations, which is sort of a big part of my work, which is looking at particular things in the course, and I'm focusing on things that cut across the curriculum, such as Taylor series, complex numbers, and so on. Things which you'll see multiple times, things that are important for them to pull out, and doing a think aloud study with think aloud studies with students. The other piece of that is this conceptual diagnostic, which has been designed and has some interesting issues associated with it that we'll talk about in a moment. This is an open-ended survey. It's much like the CUE, if you're familiar with that. And the idea is that the questions or the problems that are on it are directly connected to learning goals. So here's an example of something that I've done with students for Think Aloud. So this is let me just sort of sketch it out. This is a cylinder here of radius r. There's a small spherical mass down here at the bottom. And the students are given an expression for the potential energy as a function of the angle which the sphere makes with that cylinder. And then they're asked to find an approximate expression for the gravitational potential energy near the bottom. And then comment on that physical significance of that result. And if you were to work this out, you would get something that I've chosen 0 to be here, and the first non-zero term is phi squared, so it has some sort of harmonic oscillator look to it. And in fact, students have a lot of trouble with this. In particular, they don't cue on this wording, find an approximate expression. For a number of students I interviewed, that means plug in 0 and get 0. And with a little coaching about, what does it mean to be an approximate expression, where does that mean when looking, that kind of stuff, they can eventually get to this idea of Taylor series, which leads me to believe that we need to do some work on this implicit cueing, how we actually get them to sort of think about when is it appropriate to use this Taylor series.
They see the phi equals 0, but they don't cue on the word near phi equals 0.
That's correct.
Yeah, that's what I'm wondering about. I mean, is there a way to be more explicit about what it means to be near?
Yeah. So,
Did you ever say first order, second order approximation?
So this isn't the only. Yeah, this isn't the only question which has been asked, and other questions which have more explicit cueing they're able to do. So, things that say explicitly use a Taylor series, or things that say explicitly to first order, something like that. There's different words which one can use, and there seems to be degrees to which they use.
So you're going to get into this, though, in more detail. The difficulties that students have from Think Alouds, or no? That's a different.
No, it's a completely different topic.
That's a different talk that we're going to ask you to come back with, because I think this is fascinating, because this is this matter of cueing. What is it that drives people? When do they know when to do things? In fact, I could even imagine saying, the reason you do Taylor approximations is that they simplify a problem. But, I mean, to students, maybe that is simple, and it's more complicated to have more terms. It's a functional expression that I plug into my solver, right? And it's perfectly reasonable, and so there's this whole culture among physicists to be able to say, no, I know what simple means. Simple doesn't mean the smallest number of terms, but in fact the driving terms, so I get it at, sort of physical
Simply starting to understand what physically is going on.
And then there's the mechanics behind it. Anyway.
Right. So there's a number of other things I can mention here. So not in this particular example, students seem to have trouble with which is a small parameter. We see that in homework and on exams, questions that we've designed for that. They have trouble with doing any type of Taylor series that's not around 0. They also, one of the things that's very interesting is they do the full Taylor expansion of that function. So they don't cue in on the cosine part, the sort of optimized way of doing a Taylor expansion, which we tend to do a lot. They do the full functional form, which is how they were taught in mathematics, and that's sort of the piece that they are, able to regurgitate. The other.
What do you say they do 1 minus cosine?
They use the full derivatives. They have u of 0 plus u prime of 0. So any functional form that I give them, that's the way they tend to go. Even if there's a polynomial term in here, they'll take derivatives of that, which is not a bad thing. It's just an interesting way, and it's not often.
It's a formalism.
It's a formalism.
And this is yet again mathematicians screwing with our undergraduate physics majors. I'm kidding, but it's this math, physics, discontinuity at some level.
Yeah. Something I've noticed when your function is a polynomial, I've noticed that hardly any students understand that a binomial expansion and a Taylor expansion are necessarily going to give you the same results.
Yeah.
You know?
Yeah, they're sort of treated differently.
They're
That's
thought
right.
of as like, this is binomial is here, and Taylor expansion is over here.
Yeah. Yeah. And the sort of the last piece of this, which I'm sure we see, I mean, we see in every course, is the ability to interpret what they actually get. So there's sort of this feedback loop of, what was I trying to get in the first place? All right, how does that connect to what I know about the physical system? In fact, of the 4 people I interviewed, only a very, very strong student was able to comment on it. And eventually they all actually got to something that had a phi squared in it. So, and there are other questions that have the same sort of comment on the physical significance business, and they just kind of say, well, the equation is this. And anyway. All right. So here's another what are students learning sort of question. This is a question out of the CCMI. It's a 2D potential energy graph with hills and valleys and so on. And some of the questions are, for which of these points A through F is the particle in stable equilibrium? Please explain how you decided on the above answer. And the learning goal that's connected directly to that is students should be able to recognize equilibrium points on the plot and determine if these points are stable. So you can see here that we've sort of directly connected the way we're assessing this learning goal with the actual problem. Okay, so this assessment has 13 questions on it presently, which is far too many for students to do in a reasonable amount of time. So I've been working with faculty and chatting with them about, what minimal subset of these questions do you think are useful, which questions do you think have problems, and so on. So I made 20 copies of 2 problems, which faculty highlighted as being troublesome, or they didn't like, or...
Enough for everyone?
I do, hopefully, if there's...
Oh, we could share.
Yeah, I mean, there should be enough. So it's front and back. And what I'm looking for here is for you guys to maybe give me some guidance, maybe some ideas. Anything that you say is useful, nothing is stupid. So I'll give you some time to read over them, and then I'll just mention what faculty said about each one, and then we can sort of chat about that. Did everybody get a copy?
Nice. I like these questions.
Yeah. All right. So I'll just maybe talk over you while you're reading. So if we look at question 2, which is this astronaut question, the faculty members that I interviewed were pretty consistent that the question sort of going about the question is asking the wrong question, or it's posed in sort of the wrong way. The idea being that what they think is interesting is, can students, again, activate Taylor series? Do they know that they should be doing it? And then what parameters should they be doing this with? So they felt in general that there was way too much hinting, that they'd like to see what they could do with it, and if the question was posed in such a way that it could elicit that, they would be happier with it. They generally went on and said, well, I want them to calculate it. And I think, in my opinion, and I think probably it speaks, we want to sort of avoid that piece. I mean, this is a qualitative exam. We don't want to do a lot of calculations. But that was the idea, so I'd be interested in hearing your input.
Well, calculating anything takes up too much time, and we want as many questions as possible on the exam. So,
Right.
just from a practical point of view, I would say we need to avoid having students calculate.
Too much calculation.
It could eat up 20 minutes.
And the final exams can certainly have a question where students need to compute the Taylor series so that the faculty members can still assess whether students can actually do the calculation.
I'm very interested in distinguishing here between do students know whether they should set up a Taylor series, and can they set up the Taylor series, and then can they solve the Taylor series? And I suppose there's the fourth part, which is can they interpret the results of the Taylor series? I think each of those are great questions to be asking, frankly. We've only asked number 3 historically, near as I can tell, is do the computation. Maybe a little bit, all of them by saying, giving a problem with no explicit hints that they should be doing Taylor series, and then watch them flounder. But then we don't get any information as to whether or not where students are being challenged. So I like the idea of breaking it down, asking more targeted questions. So this is a perfect, to me, well, not perfect because I haven't read it in detail, but I assume since you were involved in this that it's perfect. That this is really good at getting at the second point, which is can you set up a Taylor series?
Right.
Are there other questions about assessing whether or not students know when to use a Taylor series?
It seems like one of the things to do in this question, though, is you want to first manipulate the equation a little bit to see which are big and small terms, right?
Well, so students don't do that. That's one of the questions that's left out, because at present we give credit for a student saying D or a student saying R minus D. So the question of whether or not the thing is small compared to what, that question is not graded, and it's not asked.
Right, so I guess if faculty are unhappy with this question a little bit, maybe you could reframe the question instead of asking what you asked. Maybe manipulate this and give your reasons for what you'd expand around, something like that.
Yeah.
That you could see that first step of how are you deciding what's big and what's small, and what information are you using to get there.
Why is D a correct answer?
That was before me. That was selected to be a correct answer. So there were meetings with faculty about what should be the correct answers for this.
Yeah, D is small compared to R. So there is a real sense.
D over R.
D over R is the unitless parameter, which is small. D is a small parameter when compared with the natural scale of the problem, which is R. R minus D would not presumably be a small thing.
I guess that's right. So, I mean, there is also, so this whole thing, this has a lot of work, and I'll mention what work needs to be done to it at the moment, but one of those things is what are actually the acceptable answers, and how do we give partial credit to answers that are not the correct one.
It seems like you don't want to expand in D because, like, if you want to throw out terms, you can't have units in there.
Absolutely.
Right. Although it turns out you can. As a physicist, you can get away with it.
If I use equal to 1, then,
right.
Well, to me, I just in terms of value, now this is just value judgment, I think actually knowing when to use Taylor series is probably more important to me than how to set up Taylor series. Both are important, but if we never get to the question of under what conditions do you create a Taylor series, I'd like to see a problem there. That this doesn't help you with your instrument because it makes it longer.
And it may be that in fact that task is a higher level task than a sophomore. I mean, remember, this is a sophomore level class, and so the learning goals that we have are tuned to the place in the curriculum where the students are coming from. We are still not at a stage where we're asking students to decide whether they should be using a Taylor series. I mean, pretty much we are still providing that scaffolding. That will come later, when you have multiple ways of approximating something and deciding that Taylor series is the right way.
But it also makes me wonder if it does come later.
Pardon?
It also makes me wonder if it does come later. Like, do students who are, in ENM 1 or ENM 2, are they able to do that?
I think we might be, this is a learning goals thing, but I could easily imagine that by not having that as an objective for this class, and I would have a different objective than you do, which is to say, do students know when to use an approximation, and the only tool they've learned for approximation in this class is Taylor series, perhaps, not which approximation to choose among. Those are different questions, but I could imagine that decontextualizing Taylor series in that way, which is you never have ownership over determining whether and how it's appropriate might make it more of this rote algorithm for the students.
Danny, can you say a little something about how students do perform? I mean, so faculty are unhappy with this, you said, because it holds their hand?
Yes.
Gives them too many hints. So
Yes.
how are they doing on it?
They seem to do, given the grading rubric that we have now, they do well. I mean, they
But have you tested it without the queuing?
I have not.
versus-
No, I have not. So, I mean, another piece of this is, I'm not sure, but I don't think anyone has done, I think, a lot of interview with the questions on the CCMI, maybe parts of them, but not together. So that is also something that would be quite useful to work out some of this language. Okay, well, that was really helpful. So,
Well, I think, putting myself in the place of a student, I think some students are perhaps confused by the phrase expand in a Taylor series. They have in mind that they're going to actually start doing derivatives rather than wrestle the function into a form that they recognize the Taylor series for. You know, write it as form 1 over 1 minus theta squared, and then you don't have to do any derivatives. You just remember it's 1 minus n times the parameter. So you don't actually do derivatives. You just get it into a standard form and then remember the result of the Taylor series expansion.
I see what you're saying.
And so I think, yeah, I think that particular the phrase you planned, well,
So if you, well,
Yeah.
but wouldn't that get to
Yeah.
this sort of calculating question? Like if you give them this form and you say, get this formula into this form.
right.
What is X, for example? That's a good question. I think it wouldn't take them a long time. But if they have to get it into that form, they have to do some. They have to probably do some calculation unless they sort of know.
I mean, I guess
I myself don't know how to improve the wording. So
I guess I
don't
would
know.
ask the question you're really trying to ask, which is, what is the small term here? Because that's what you're trying to ask. Put this equation, reformulate this equation into a form where you can decide what are the small variables, what are the small terms. I mean, that's what you're really asking, because that's what you expand about. So why not just ask that?
Yeah, but what answer do you expect? Is D the small term? Or
I don't
D over
expect
R?
anything, Mike. I want to see what the space of student responses is.
No, I like
But isn't
that.
that what the question
Well,
is? What
except
variable will
then
you
you're
expand
giving
in?
them like the fact that it has to be small. I mean, either way, you're giving them.
You're giving them that it has to be small, but they have to still sort of know that it's unitless, right? I mean, that's.
So
But
say
it doesn't
again
seem
what
to be-
question you thought we should be asking, Ariel? No, I mean, you
The-
had to do a slight rephrasing of this question.
So basically, what you're really getting at is, how do I manipulate this equation? I'd probably expand the bottom r minus d squared and then factor out a big R squared. And that's what we really want students to do, right? I mean, that's what we're curious if they have the facility to then look at that and see what are the terms that matter here? How is D growing? How is R growing? I mean, that's the facility you gain before you can decide what you expand in a Taylor series about, right? You need to know.
Yeah, I don't know which comes first.
What about something that's asked like, what's this variable so that you can justify throwing away higher order terms?
Yeah. Yeah,
Say that
something.
again, Charlie?
Yeah, say it again.
What variable would you use so that it would be justified to throw away higher order terms or neglect them?
So you think that's an easier question or a harder question?
I'm wondering if maybe it's getting more at
What you're asking,
really.
and then not
Well,
queuing.
I mean,
you're queuing in a
you
different
you
way.
also asked for what variable. You just changed, instead of will you expand in for your Taylor series to what variable will allow you to throw away higher order terms in that variable.
Well, it's just,
in an
I can
expansion
expand
which
it.
will
I can
be-
expand it in anything, right? If I keep all the terms,
That's correct.
right? So, I mean, we're really, if we're talking about approximations, and it's always a justification that I get rid of higher order terms because I'm using a small parameter, right? Something that's small compared to 1 or something like that.
But Jerry, I thought that in fact you were interested in seeing whether they knew Taylor series or not. So,
That's
have you thought about changing it to what approach would you use?
Yeah, I have thought about doing that. I mean, that's something I want to.
Predict the difference.
That doesn't. I think that doesn't go with this topical learning goal. It goes with the course level learning goal, right? Because the topical learning goal is that they should be able to compute it. They know what vector to expand it. So that learning goal leaves out the idea of students should be able to identify when a tailored. That's a course level, which I'm open to. I think it's an interesting question what they're able to do that, but maybe that's something we don't do on this.
Yeah, I'm just reading the learning goal. It says specifically, how many terms do you keep, right? And for what values, is this a good approximation?
Right. Yeah, I like your phrasing, and I think I'll have to think a little bit about that. But I like the way that you guys are framing it a little. Okay, so let's flip over to 9 real quick, and this one is quite a bit more troublesome in the sense that I don't think that the question connects to the learning goal at all. That might be a fault of not a fault, but that might be just the learning goal is maybe too specific, or I'll let you look at it again, and then I'll just say the faculty said about it. So most of the faculty like the learning goal to some extent, but they really just don't care about how students are able to reason that those points, say B and D, are stable equilibrium. They just don't. They think that they can do that from a number of different ways. Thinking about sort of a valley, or thinking about a bowl, or even talking about forces if it were to go up a little higher or something like that. They don't see the need for the Taylor series in it at all. Yes. No.
I think this is a fabulous opportunity, though, to address a different learning goal, or a related learning goal, which is the math-physics connection. And the answer, this is sort of a classic LB approach, or DeSessa approach, which is you already know what the answer to this is, where the stable places in this. You know this from your intuition and your life experience. But now come up with a way of describing this to me. Okay, physically, fine. You perturb it, and it's going to end up in this situation by exerting forces, and it's, or you can look at energy states in the system. But now I want you to be able to demonstrate that to me rigorously mathematically, and that's what the Taylor series can do for you in a particular way, I think.
So Danny, is there objection to this that they don't think that the Taylor series is necessary, or they don't think that this question is eliciting the Taylor series explanation?
Taylor series explanation is not elicited except for the added phrase, now please refer to Taylor series in your explanation, which is a cop-out.
That was absent in the first year, and so we didn't see it.
Right. And
so why not do something that instead says, for which of any of these points, taken a leading order, will give a potential that yields, and give them the equation for simple harmonic motion, give them the potential for simple harmonic motion, don't say simple harmonic motion. Would that get more towards it? Because then they have to make that. They have to make the connection that, oh, that is the potential for simple harmonic motion. It must happen in these cases. Do you know what I'm saying?
yeah, that's interesting.
I feel like there's a lot of visual cueing going on here.
Yes.
I don't have to know anything about
That's right.
the actual
Yeah, and that
anything. I just look at the potential.
that's the sense I get from it,
Obvious.
is that there's sort of this graph that strikes you as giving you everything that you need to answer this question, right?
Right, but if you didn't say simple harmonic motion, then someone would at least have to recognize that that potential is the potential for simple harmonic motion. That connects to these stable points.
That's true.
Do students know also that those are the conditions? I mean, this is another question, that lead to stable equilibria?
I have no idea.
We have a separate, isn't one of the first questions on the CCMI? It's basically asking them about simple harmonic motion in graphical form, in potential form, and in force form.
About half the students draw something that looks sort of quadratic-y.
Right.
The other half draw something that looks sinusoidal.
They draw a potential.
They draw a potential that's sinusoidal. So that's another reason to do one of these think-alouds, to see if they're thinking of time or if they just don't know what that means to have position.
Oh, that's interesting. What if this graph was sinusoidal?
Oh.
Clearly, physics have a different sense of humor.
Well, I mean, to me, I want to go back to this, though, which is, do any students ever get this wrong in terms of where are the stable equilibria here?
But you mean the...
Like picking points B and, I mean, forget the math or any of those statement. If I were to simply give this to students and say, where are the stable points in the system?
Some pick C. No,
Well-
but some pick C.
So if
Okay.
I were to look at this, I would be, from my completely naive biological perspective, I would assume that this is a system in which there's thermal fluctuation, and so it's not clear that, who's stable would be determined by the size of the fluctuation. Because I could say, well, I'm
Right.
going to kick it out of B and C by banging it around, and it would go fly off past onto the left side of the curve. So so I'm befuddled.
Right. So the
Right.
so the
Right.
piece here
It's
is
leading order.
Yeah, leading order. It's small. What's small?
But also there's the physicist assumes, uses the word stable, implies locally stable.
That's right.
And the mathematician would say that, well, do you mean local stability or global
Well, actually,
stability?
stability is not asked for in this
Yeah,
question.
where's the word
Asked for-
stable? Sorry.
Nowhere.
The question specifically says,
Oh, yeah.
There's no.
where can the Taylor approximation to leading order give a potential that yields simple harmonic motion? So it's certainly an unambiguous question. I mean, I think we were hoping to elicit student ideas about physicality, just to see whether they're thinking about it physically. But in fact, I don't believe we got that. Students answer this with the sort of WYSIWYG simplest answer.
I mean,
What about asking more like what the principles behind this is that? I mean, first of all, we want the first derivative to vanish, right? And then, we have like a squared term that goes positive and so forth. I mean, like those are kind of, I want to identify, these two things that are, giving me these.
So I'll say, so if you maybe this is another way, if you decontextualize this, I don't know if you correct me. If you make this just mathematics, they do very, very well on that kind of reasoning about derivatives. Even the students who don't do well on the physical problems, they can tell you that the function is zero, the function's first derivative is zero, the function's second derivative is positive or negative. They can reason from the graph very easily.
then maybe you could say something instead like,
That's from the Think Aloud study. That was another question.
gives a potential that yields a linear restoring force.
That's interesting.
I mean, because that's what leads to simple harmonic motion. So then they have to really make a math physics
Right.
connection.
Yeah, that's
Right.
I like
And then
that.
XA will become very tempting
yes. Yeah, that's. I like that.
Oh yeah.
because it looks linear there.
Yeah. Right.
Great. Okay. Great. Well, thank you very much. We have a little bit more, and then I have another handout for you guys to do more work for me. So here's sort of the halfway point. Here's my to-do list. This is the stuff that Steve and I are working on this semester. So I broke this up into course focused and assessment focused. So we're continuing to work on materials. We were just doing that earlier. So going over materials that we had developed previously and trying to improve them and expand them. One of the things I'm interested in is external validation of learning goals. So people that are at other places teaching this type of course, what do they think about our learning goals? Because if this is going to be something that we claim can be used in other places, we need other people to tell us about what's going on, what they think about it. And we're, organizing and archiving materials. I'm not doing that, but I will do that eventually. So now on the sort of assessment side, there's trimming of the CCMI that is making it shorter, so that students can take it in a reasonable amount of time. There's a variety of validation methods that this still needs to go through, and then reliability calculations, broader adoption and measurements, and so on. So there's still a lot of work, I think, to do on the CCMI. This next sort of thing connects to the direct investigations. I started sort of dabbling because of Noah really in theoretical perspectives, how someone sort of breaks up complex tasks. And so I have a theoretical framework that's sort of functional for a Taylor series, and it's kind of, maybe one day we can talk about that. It seems to be leading down a very nice road, sort of telling me what subspace that students engage in when they're doing Taylor series, and what subspace experts engage in. And there's other direct investigations, and if you're interested in helping out in any way, I'm more than happy to have you help out. So, first year graduate student. So I want to turn back now to this question, which is what should students learn? And this is something that Steve and I talked about when I came out here the first time. And it's actually disengaging faculty to an extent and asking students, what do you think you should learn? And those of you who talked to me for any period of time know that I'm very interested in computational physics. And so one of the things that we asked students last semester, we surveyed students in all of the major courses that faculty would let us. We got about 65 responses from students. And one of the questions we asked was, how is it important for you to learn computation, which we define as part of your development as a physicist? And this graph sort of boils it down, but 75% of the students which we surveyed recognize that it's essential or important for them to learn. And there's more details here. I can send that link around if you guys are interested. There's a lot of other questions which we asked, but most the upshot is essentially that students think that this is a tool that they need to learn to be successful either in the industry or when they go on to graduate school. And it's something which they don't think should replace any of the things they're doing in class. It should be something that's coupled to the class, and so they can sort of connect the computational aspect of the course to the theoretic part, to the lab part. Ben's not here, but he can talk to you about that too. So this is sort of a motivation to develop a systematic way of instructing students in computation, and still not pulling out too much or replacing too much.
What do faculty say?
The faculty who I've talked to about this seem to be on board, but I haven't gone very far with it. I talked to a number of people in the group, and then a couple of people that have taught the course.
You said you define computation.
Yeah.
In the question, how do you define it?
I define it as using a computer to solve a science or engineering problem. Not graphing.
Like, how long does it take for a computer to fall from the 4th floor to the...
That was the first question.
I think one of the reactions that I see when talking to other faculty, and maybe have myself, is that most faculty are sympathetic to this, but we also recognize that we have this constrained system which already is packed to the gills. And so a lot of times the question is, well, what goes?
Right, I think it's a question of mechanism, actually. I think people would agree with this as a goal, and then the question is, does it sit as a separate piece? Does it get integrated? What are the methods by which we do it? What is it that gets displaced in order to do this? So some people would say, hey, our classes are all about really learning how to use differential calculus effectively, and computation doesn't help with that. Or some would say do. I mean, so I'm willing to bet that people all agree that it's important, but that's not in a comparative sense or in a mechanistic sense. In what ways do we go about it?
And then there's logistical questions like, if we agree as a department that it is important for students to learn computation, and then that means that we add a computational physics course, when does it happen in the curriculum, and how does it get integrated into the other courses? So the sequence right now is very well established, so that when you teach junior E&M, you think you know what the students are walking in the door with. At least you know what prerequisites they set.
It's even worse. I mean, we've maxed out on the number of allowed physics courses that can count toward graduation. So the only way we can add a computational physics course and make it required is to remove one of our required courses. So it's not only addition, we actually got to swap.
Which I think has led Danny and I to think about, incorporating it into pre-existing courses in a sensible way. But the question still remains, when you get to a junior level class, can you count on all the students in your class having been through that pedagogy? Because every faculty member gets to do whatever the heck they want in sophomore level classes.
Right. So luckily, we are only working in one course right now. But the idea would be...
And you're in charge of it.
And then, I guess so. So then the idea would be to make this somewhat modular, so that faculty members can choose to include it or not when they're teaching this course, and then dealing with what might be done in future courses. It might be a lot of circling back.
I might also emphasize, at least this department has a fine tradition of the faculty then saying, oh, you can demonstrate to me that that's a good idea. You have evidence behind this, that this is both plausible approach, here are the materials that we can use, and that it's valuable through forms of assessment that you do. So it's plausible that we could use this as a form of change for the department.
Is there a math methods course, or is this
That's this course, classical mechanics.
Methods course?
This is certainly the natural course to introduce this.
And do you?
Introduce it?
Do you teach the students mathematics?
Yeah, every homework assignment this semester will have some computational element to it.
Right, but how do you teach the students mathematics?
Well, we are teaching them Mathematica by giving them homework problems.
So this
and tutorials.
Let me lead into this. So,
okay.
So this again, this mirrors the same framework that we talked about a moment ago, Mike. So maybe this makes sense. So what should students learn? So I formed consensus learning goals, and I will show you who my counsel is later on because they're not in this room. So here's a core scale example. Students should be able to perform algebraic manipulations and solve algebraic equations using a computational tool. So it's sort of the same sort of mirror. It's very broad. What does that mean when we drill it down? Students should be able to find the roots of an algebraic equation using a root finder by setting appropriate neighborhoods. So now we have something that's measurable that we can go in and test presumably. So these again were developed last semester, and we can change them. We can look at that. What instructional approaches improve student learning? So what we've been using is what I'll call a somewhat circular design. Steve and I are revisiting the types of tasks we're asking students to do throughout the semester. So they use some plotting, they go back and they do plotting again. They use ND-solve, which is a numerical differential equation solver. They use it again in a variety of ways. And we're fading the support. So we start off with a lot of help, and then we stop pointing to this help, and we start just asking them to do things. So that's sort of the plan for this semester, to be more systematic about it. Let me point to some online resources. So here is something Ben and I worked on over last semester and over the Christmas break, was creating a suite of screencasts in which we teach, or not teach, but in which we show students how to use various approaches in Mathematica. This one is writing for loops, but there's plenty of them out there, and they're all at CompViz at CU on YouTube, and we have hundreds of hits now already. So I can play this for you, but it's just
Good job, Steve.
Danny.
Just me talking.
No, he's one hitting.
Oh yeah.
No,
Oh, how do you do those for loops, man?
Well, I did use it last night.
So, so here's another sort of instructional approach. This is one of the things I want to get feedback on. So I don't know, what the formal way of talking about essentially learning from an activity or a real-world problem. It's problem-based learning or case-based learning. I'm not sure what it depends on which school you're actually in. I think in this College of Sciences.
How it's set up. Yeah.
Right, and so this was a problem that we had students do last semester. So here's a video which I'll play for you really quickly. It's essentially
Pretty obvious.
So it's a viscously damped oscillator, and I pulled this video into Tracker, which is an open source video tracking software, and found the position as a function of time. And then
Sorry, I don't understand what I'm looking at.
this is let me show it again.
Huh.
Yeah, so it's oh, I can do it from here. So it's a damped oscillator. There's oil here, and there's a damper inside of it, and there's a little point here which you can track. It's hard to see.
Yeah, is there a spring somewhere?
Up above.
Up above.
I see. The spring is above the frame.
Right.
Okay.
Right. So the idea was then to have students bring the data in which we collected, the position versus time data, and try to connect this now to the model which they have, which is this damped harmonic oscillator model. And so here's actually, this is my solution. The student solutions were actually very good. They were very close to this. We surveyed them after the fact, and they very much enjoyed this type of problem because they felt that it connected directly to the type of physics that they're learning, and they saw exactly why they're trying to describe this physical system. They started to sort of internalize it. So I'll let you guys, this is a really long question.
Can you just walk us through it real
Yeah,
quick?
sure. Let me just do that. So the first part of the question is essentially, right, so, look at this video, and then the second part is write down the differential equation for a damped harmonic oscillator. Then here's a plot of a damped harmonic oscillator with some parameters. And then the rest is essentially parameter scaling. Ask them to peel out from this graph. What are estimates for those parameters, and how do those parameters affect the graph? And to sketch that and discuss it. So that's the first part. That's sort of the setup.
So page one, after the setup, all the rest of page one is all the same kind of homework that we could have had before any computational or real-world connection.
Absolutely.
It's all sort of formalism and plot understanding.
Right, plot making sense and so on.
And just also for the record, then the computation that you're having them focus on is creating a plot of the differential equations, solving this differential equation versus time, but not fitting the data, which is to say they're supposed to estimate what the parameters are. The computer doesn't go through and do a fit.
That's correct. They are estimating. So this is the setup for understanding how those parameters control the graph.
Right.
And then when they have this plot of the data, they can then try to figure out what the initial condition is and then sort of
Right.
scale things efficiently. That's the idea, is that they scale it efficiently. And in fact, this question didn't take them more than about 30 minutes or so. That was a self-report. So that's.
Do they create the model? Or do you?
So
I guess it depends how early the semester
the initial, this is near the end of the semester. The plan was actually to have them numerically solve it, but it turns out that this is such a well-damped oscillator that the linear term is the only term you need.
Right.
So we decided to just have them plot it, since we were already having them pull in data and everything else. But the idea would be that Steve and I created a couple of other of these types of problems where students would play with the models and take real data.
Right, if you change the physical setup, it may be that this linear model doesn't work so well,
right.
And it would be nice for the students then to
dropping a penny on somebody's head. Right.
That's what
to
we're
have
doing
to
now.
decide right what is the model. But it seemed like scaffolding, this was the first activity.
Yeah.
Is give them the model and have them understand how the parameters of the model are reflected by the data.
And a lot of the scaffolding that's in this problem, I imagine it going away, because now we're being more systematic about it. So we have a lot of screencasts and things like that. So we can remove a little bit of this, make it a little shorter. So that's sort of what opens up when you start to be able to use, or when you start using computation in the course, you can start to do a lot of different things that you couldn't normally do. All right, so this leads me to the sort of last question. What are students learning? So this is what we're working on right now. The first thing is maybe we get some computational confidence. There's a lot of literature out there, and there's a lot of work that I did at Tech that tells us that students are still, even after a semester worth of instruction on computation, they're not comfortable with it. They don't like it. They don't feel like they can do it. There's a small number of students that feel that they can do that, and that hasn't been characterized here, but we plan to do it using this student assessment of learning goals, which we just iterated on this weekend. The other thing is computational proficiency, which I would actually call a traditional assessment. That is, you have a set of learning goals for which you want students to be, or a set of goals that you want students to be able to achieve, and then you design an actual activity which achieves those goals. Are they able to do the things that you asked them to do? And I haven't talked to Steve about this, but maybe we could do a proper discussion. So I don't know, we'll see.
There's 80 students.
Yeah. Then the other thing which I think is completely different is this idea of computational modeling. That is the design, use, refinement, and testing of a model, which I think is higher level than this proficiency. And we are planning to do that with this sort of scaled-in final project, which we're going to have students do, where they essentially design a computational model to investigate something of their own interest. And so we're planning to do that in the last 4 or 5 weeks of the semester as part of their homework, and the last homework assignment would be to sort of put it all together. And then finally, this piece, which is mirrors what you would do with other student difficulties, is looking directly at what students are doing and trying to understand where they're having trouble. How can we intervene and make it simpler, or make it more straightforward, or provide them some additional scaffolding. And so in my experience, limited experience in PDR, these things are completely open. I mean, I don't think anyone really worked on that in a lot of detail. So it's very, very interesting work, I think. And then I guess finally, I just want to thank a lot of people in helping me, Ben, Noah, Rachel, and Steve, and then my computational counsel, all these fellows I know from either Twitter or that's basically it. So thanks for all your help. Questions, comments, concerns, Noah?
I'm going to defer though to other questions first.
I was just going to tell you that I know that Joe Reddish and Tom Bing had at least one, maybe 2 papers on students solving quantum problems with Mathematica.
Quantum problems?
I think it was quantum problems.
Okay.
So it's Bing and Reddish.
Okay. In Mathematica, really?
Mathematica.
Okay, great. Noah?
I'm still giving it weight, son.
It's a very important teaching.
One curiosity I had was when I took grad E&M, Tom DeGrand said to us, Stephen Wolfram does not take this class. because people were using Mathematica to do, I mean, some of these Jackson problems, you have these enormously tedious algebraic manipulations to do, which I think some physicists would say are good mental push-ups. So is there any feeling from the faculty of...
There's a feeling from Tom.
Well, I mean, of how to use this computational tool, because I understand what you want to do with it. You want them to see how is this used in the real world, how do physicists use computational tools, how can you get deeper understanding of problems from this. But I do think there is a danger, I mean, I do see Tom's point in that there's a danger that sometimes students use this in a way that kind of offloads some of the work you need to do to gain facility with mathematics.
Yeah, someday they'll be using calculators for the easiest of arithmetic problems.
They already are.
I know.
Right. Oh, yeah.
That's my point. Yeah. But I mean, your point is well taken. Tom is not the only faculty member who's worried about that.
Yeah. I'm just curious how they're feeling about it.
And I think I actually suspect that faculty will have strong disagreements about the extent to which it is damaging to students to have them rely on computational.
So I guess if I see
for
one of your transformational goals is to have sustained transformation. So it seems like that's important. That the way you frame how you're using this tool isn't as a easy way out for certain kind of math problems. I think it's real important for the faculty here that
the way that I might frame it would be something like it's an extension to what we're already doing, right? It can help us to make models richer and help us to explore problems which can't normally be explored. And I think you have to be explicit about that when you are starting your course and in every homework, which is what one of the things that Steve and I were thinking about when we're doing homework problems is whether they're going to shortcut and how we keep them from.
Yeah, I think what can't be divorced from that is sort of the sense making that goes along with that. Because I think the biggest problem I see with students who are using Mathematica is that they just automatically accept that the answer is correct. And they might spit out some amount of gobbledygook, that you have to maybe take several steps to massage it and put it into a useful form where you can get some sense out of it. But I don't see students do that hardly ever.
Right. So to play on that just a little bit, so I don't plan to use it, I don't know, Steve can chime in. I don't plan to use it as something that you use for symbolic methods at all. I plan to use it as something that you can use with data, that you have to solve, something that you have to do numerically, and something that you have to use to interpret plots, really. I mean, that's really the key piece of any computational tool, in my opinion, is the visualization. How does that visualization help you to understand the physics? And so I think the problems that we've developed thus far do that. I can't think of one that has been written that does any symbolic manipulation whatsoever.
I think that's great.
So, I mean, yeah, Katie.
So when you had the graph about like the students, they say it's essential or important that do you ask them specifically like what programs they think they should use?
Yes, we did. So maybe I can go to this link and sort of show you, because that was pretty interesting.
So I would guess students would expect out of their undergraduate education to know, to be prepared to go do something and to know, at least Mathematica,
right.
At least, some kind of object-oriented,
world. Right. So we asked them to characterize the tool, not to actually tell us what it was.
Yeah.
So this question, if you can't read it, says, in choosing a computational tool to learn, what are some important factors other than my professor chose it that you might consider? And the number one response is the tool should be easy to use. There should be a significant amount of resources to support learning the tool, which we've tried to do. The tool should be powerful and efficient. Now you can argue if students understand what powerful and efficient is. This was an open question too, so students wrote their responses. We didn't give them these responses. So this is what I pulled out of that. The tool should be flexible and adaptable. You can again argue whether they understand what that actually means, but the tool should be well accepted in my field. So they don't want to learn some Mickey Mouse language. They want to learn something that they're going to be using when they're done. Python, Mathematica, MATLAB, something that professionals use. Lisp.
Yes, Fortran.
The tool should be cheap or free, and that's a little surprising that it was so low. So they are willing to pay if it's something that's going to carry them.
Sorry, what was the top one again?
The tool should be easy to use. Easy to use. We asked them directly, how important is it for you for the tool to be open source? They were fairly neutral as to whether it should be open source or not. They didn't really care, as long as it did the things that they needed to do. how important is it for you that the tool be available for you after your college career? So this is sort of getting at the open source question, but in a different way. And most of them think that they should be able to get it easily after they're done with college. So this sort of subsidization of the tool in college bothers me a little bit, because once they leave, where are they going? Are they still going to have access to that tool that we've taught them to use?
We're using Mathematica, and it's free to them now, but they'll pay to
Yeah, but
No, because they'll use it in a job, which will buy it for them, or in graduate school, which will also...
Or there'll be, I mean, the other more important thing is that you're teaching them habits of mind around computation, so the language is going to change, ultimately, too.
Wolfram Alpha is free.
Yeah, I mean, that's what we should all do. So then we defined easily available. We asked them to define it. They said under $100 or free. So, and then somebody did say, as you mentioned, Katie, provided by my employer. So again, if they go somewhere, if they go to one of these R1 schools, if they go and work for a big technology company, they're going to have access to these closed source tools. So maybe that's not a big worry. The thing that I'm worried about a little bit is teaching them to use a tool which is very high level, like Mathematica, and not lower level, like a programming language, where they have to sort of construct how the algorithms work. But that's a completely separate issue in my opinion.
I think that's a...
If you poll the people who teach graduate school classes what they think the students should know how to do, I would guess that all of them say they can use Mathematica. I mean, most professors would assume that incoming graduate students can use Mathematica, even if that's not true.
Yeah. Or learn it on their own. I mean, to me, this is the really important thing. I think this last point that you brought up is a key distinguisher, though, too, which is how high level is this? For instance, does this say solve, integrate blah is fairly high level, as opposed to you're teaching them, this is the other computational work, is teaching them stepwise processes and integration.
We're finding, Steve and I are planning to do that, maybe, because Mathematica is really annoying in the way that it deals with for loops. So if you want to teach this sort of stepwise piece to unwrap the differential equation solver and say, this is how it's trying to do this, and this is why we don't write it this way, that's really tough, because the syntax is really, I mean, and again, I'm a Mathematica novice, and so maybe it's actually easier than I thought, but it makes it tough. So having a language that's high level enough where it's easy, I mean, I don't know.
So was the Mathematica choice driven by that?
I wouldn't say that. I would say that it's a practical choice, because it's what the students have for free, and it's what faculty are probably comfortable with.
The CU faculty have talked about it in faculty meeting.
Right. We moved from MATLAB to Mathematica.
Yeah. So yeah, partially faculty, but also I think it's practical. It's really
What was the
available.
reason for moving to Mathematica?
Pardon? What's
What
that?
was the reason for moving from MATLAB to Mathematica?
It's free.
Free.
MATLAB, you don't have
For the
MATLAB.
students.
On this campus. Yeah.
Right.
MATLAB's not free to
No,
students.
it's not free.
Have you looked at VPython? Yeah? No?
I mean,
I'd say it's at about the level of MATLAB.
yeah. I mean, so I would argue that you could do all the things that you can do in Mathematica, you can do them in Python, but
Right.
that requires.
Well, this is VPython.
Right. But that's a
different.
segue. That's a gateway
Yeah.
programming language.
Yes, and actually VPython can import Python libraries, so you can use numerical differential equation solvers from Python in VPython.
Yeah.
So I mean, all
I
those-
just mean it's free.
it is free. Yeah. So I mean, yeah.
So I just wanted to return to. I'm going to make my points because then I got to leave with Kathy, I think.
We're getting close to time.
Comment on sort of Ariel's question, or they may call it the Degrand question or whatever, which is perfectly reasonable. I really like your answer, but I would also, another point is, students are already using calculators or computers or solvers. So let's acknowledge that for our students and teach them when and how those can be most useful, on the one hand. And then the other is, I would argue that you can teach some of those skills that we really do care about, Charlie, that you care about. I think the same thing is true in closed form calculation and brute force calculus as found in numerical solvers, which is students get answers that don't make any sense and don't bother checking on them. So this is what we can do using this, and the approach that Danny's taking is one that will allow us to teach those same skills that will enhance students' capacity for doing those traditional form of closed form problems that we like to do in math, and we should be careful about that, and then also know when to make the difference. So I think you can answer the question. It was sort of brought up before. I was just sort of expanding on that, which is to say this can enhance what it is that we're already doing and what we already value. My question for you is, well, another comment. Briefly, I wouldn't call this problem-based learning, and not according to the literature that, unless it's sort of an open-form problem like, describe the motion of this object in time and space that you see in front of you,
Okay.
right? That's more of a, at least from the classic literature. But it also suggests that you're developing along the way, this goes on the theoretical side, a model of what it means to do computation in these environments. And there are all these various steps. So you and I have talked about sort of building out the space of work and solving Taylor series expansion. I think you probably very much want to do the same kind of thing in computation, because there's all kinds of things that you're scaffolding students on here as well as not. And you want to look at how do students know when to use a numerical solver? What are the appropriate parameters to focus on along the way, all the way through to did it make sense? And so I think that you have really good opportunity to lay out and say, aha, here's a problem that scaffolds 8 of those 10 things that I really care about, and I'm leaving the other 2 for the students to show me, because this is where we're backing off. Do you have plans to do that?
I had started that, actually, and I set it aside because it wasn't quite fruitful, probably because I didn't sit down and talk to you about it.
I think it'd be very, very valuable. And you don't have to make up this. I mean, this is where other people must have done a lot of thinking about the nature of computation, and it may not be in physics. It's likely done in other disciplines where we could beg, borrow, and steal.
Yeah, great.
Is there a way to teach some of these skills are saying divorced from any specific programming package, whatever?
There's a lot of thought that one can do that. That you can sort of ask questions like, what is computable, right? I mean, what defines what's computable? And can you teach people to? The word that's thrown around a lot is computational thinking. It's a horrible word, but it basically means you understand what is computable and how that works. And that is really in its infancy. Trying to understand if you can again take away the computer or take away the language and teach habits of mind which make things computable. It's in fascinating literature, but there's nothing practical that actually come out of it.
It just seems like there's some drawbacks, focusing specifically on mathematics.
I agree.
What are the transferable skills, that you learn from mastering mathematics?
Yeah, and there's been some attempts by us to scaffold that a little bit with the idea of what is a for loop? What does that mean? What pieces of that do we need? So the for loop, I didn't show you guys the video, but the for loop screencast that I have doesn't use the Mathematica syntax until after it talks about the plain language, like what are the pieces that you need. So what is computable? And that's something that you can use in any language, right? A for loop is defined sort of everywhere. But yeah, I wouldn't know how you would do that yet. Steve, you want to say anything?
Can I just say that as somebody who's gone through CU's undergrad and not received any formal computational training, I'm really excited to see this happen.
But we're not done with you yet. You can be a guinea pig.
Follow the volunteer on.
Thank you guys for your time. Thanks for all your